An eigenvalue and this would be the eigenvalue of the matrix A. It's a solution of the equation AX equals lambda x. You do this for any matrix, okay? Now you should know this formally, how you get from here to the characteristic equation, which is always going to be a polynomial. First, you write this as AX equals lambda I times x. Now there's an intermediate step. You write this as lambda times IX by an associative property, very similar to the associative property for real numbers and easily proven in terms of the real numbers, okay? But you can do this. That's all we're going to say right now, which means then that you've got AX minus lambda I x equals a zero vector. And then by linearity of linear transformations, or of matrix multiplication in this case, you have this. Okay? And you get a non-trivial solution Well, if A minus lambda I is invertible, then you go ahead and invert it and multiply it by both sides. You end up multiplying the inverse by the zero vector, which gives you what? Gives you the zero vector. Well, that would be a trivial solution. We already know that if x is the zero vector, this is going to be true, right? So that's a trivial solution. Well, we have a non-trivial solution only if the determinant of A minus lambda I is zero. Okay? Because if the determinant wasn't zero, this would be invertible and x would have to be the zero vector. Well, I want you to understand this. I want you to be able to reproduce this anytime you need it, because it's a pretty simple argument. But you need to understand. Okay? Well, that's what we used. We used it in the first couple of weeks of class in R2 and R3. R2 and R3, 2x2, 3x3 matrices, right? Now you know that then from experience that if A is a 2x2 matrix, this is going to be a quadratic. You're going to get a quadratic polynomial in lambda, okay? And you're going to be able to solve that very easily. Maybe you got a real solution, maybe you get an imaginary solution, but you're going to be able to solve it, okay? In 3 dimensions, well, you're going to have lambda cubes, okay? Well, those can always be solved, okay? There is not necessarily a real solution, as with a quadratic. You can write down a quadratic where the discriminant's negative, you don't get a solution, right? Meaning you won't have real eigenvalues, okay? Rotation matrices don't have eigenvalues. Because what's an eigenvalue? Well, if AX equals lambda x, then A transforms transforms x to a multiple of itself, which is pretty obvious because that's a multiple of itself. And this is what it transforms to, okay? And any multiple of x to a multiple of x. That'd be another multiple of x, okay? I didn't write that, I wrote it this way, just to show that once you have the direction of your eigenvector, every vector parallel to that eigenvector, or along the line of that eigenvector, maps along the same line, okay? If you think of it in R2 or R3, okay? Or think of a hyperline, still one-dimensional, okay? Make sense?